Okay, what type of energy is stored when a spring is stretched or compressed? It's called, where's my other pen? Elastic. Potential energy. Let's settle in, people. Elastic potential energy, as opposed to gravitational potential energy. The spring has elasticity. It stretches out or it can be compressed. And anytime you stretch it out or compress it, it has stored up energy. You release it, it goes boing, 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 boing. Elastic potential energy. Yes.
Is it equal for if you stretch or compress the spring?
Yes. The same distance, yes. Yep. And we're going to see that with these hidden relationships. No. So, before we get started, folks, I want you to think about, where do you see springs in action? Like, where do you see springs being used? Today we're going to be looking at the hidden rules, that were found dealing with springs. So I want you to jot down 5 different places where you could think of where springs are being used.
I only know that because Mission Impossible 2. Wait, this is what Gavin Jenner playing.
Yeah.
You shoot down and it spirals out. It's like a spring. Guns have springs.
I thought tasers were like an electrical thing.
And it coils out. Toy guns that shoot like little balls.
I'm not sure.
No, they're they don't need a bullet, but they're
Alright, let's put your guns in their holsters and let's get back to work here. So today we're going to be calculating how elastic potential energy is calculated.
Can I say what Ethan said is very funny?
We're live here. Okay.
Go for it.
Wow,
Alright, so what was the joke?
So I said, are there springs and guns? And Steven said, these guns?
Oh, he showed his muscles. That's funny. Okay. So, we want to be able to calculate the stored up energy in a spring. Now, before we can do that, folks, we need to go back and look at the hidden relationship that you found yesterday in lab with the spring. So we're going to take a time out from this question, talk about the hidden relationship you discovered. It was yesterday, yes? 2 days ago. 2 days ago with the spring. And then we'll come back full circle and answer this question. So, let's say we have a ring stand. We have spring hanging. And then, let's say the next scene. Let's say you put a weight on the hanger and you stretch out the spring. So basically, folks, this was the original position of the spring, and then it stretched down to this position down here. And this amount between here and here That's referred to as the elongation. And it has a symbol X. Units, meters. And you were trying to answer the question, what is the relationship, gentlemen, between the force applied to a spring and the amount the spring stretches out. And in this case, the amount of weight that's put on the hanger, that's equal to the amount of force that's put on the spring. Usually, you're able to read from a diagram, or you're just plain out given the elongation, the x value. On occasion, you're given the original length of the spring, L sub O, and the new length of the spring, which I'm going to call, let's say, L sub new. If you're given the original length of the spring and the new length of the spring, how could you get the elongation? Because that's what we're interested in, right? The difference in the two. So the elongation x would equal the new length minus the original length. So 2 days ago, you collected data, and you found out that there was a direct relationship between the amount of force in newtons to the elongation in meters. Now, if you don't apply any force, it doesn't stretch out at all, so the elongation would be 0. I'm not going to use the numbers that you guys had in lab. I'm going to use easier to work with numbers. Let's say, for example, you put 10 newtons, and let's say it stretched out 1 meter. We'll pause here, take a break, and come on back. So, if you double the amount of force, then the amount of the elongation doubles. And if you triple the amount of force, then the amount of elongation would triple. And if you quadruple the amount of force, then the elongation would quadruple. Now, it's obvious that the force is directly proportional to the elongation. but the force isn't equal to the elongation. 10 doesn't equal 0.01. 20 doesn't equal 0.02. It's just that if you double the force, the elongation doubles. They're directly proportional. So proportionalities are good, but many times we want to know an exact equation so we can solve for different values. So if you want to make a proportion into an equation, you have to add a proportionality constant. So K here is the proportionality constant. And the thing is, if the force and the elongation are directly proportional, then the same K value will work for each and every trial. Take a look at the data, my easy number data up there, and see if you can determine what the proportionality constant would be for my numbers. What times X would give you that force? What times this gives you that force? It's always the same value here.
No. 49.
It's 1,000. Because if you multiply 1,000 by 0.01, you get 10. If you multiply 1,000 by 0.02, you get 20. But not only that, folks, we need to tweak the units because we want the units to jive. So if we have meters, if we multiply by this number, we want to get newtons. So what would have to be the units of that proportionality constant? Newtons per meter. Excellent job, guys.
Newtons per meter.
Good job, JJ.
Thank you.
So it turns out that each spring has its own proportionality constant. You could have another spring have a proportionality constant of 30 newtons per meter. And you could have a third spring have a proportionality constant of 5 newtons per meter. And basically, what that proportionality constant ends up telling you is how stiff the spring is. Whether it's like loosey-goosey, it just like pulls right out, or if it's like really hard to stretch it out, or really hard to compress. So, the official name for this proportionality constant, it's officially called the spring constant. I personally think of it as the stiffness indicator because it indicates how stiff the spring is. It's not a universal constant like capital G. Capital G is 6.67 times 10 to the negative 11th Newton meter squared over kilogram squared everywhere in the universe. This is different. Every spring has its spring constant and indicates how stiff the spring is. Now, if you graph this data, you want to do it properly and obey graphical rules. For example, when you graph data, the dependent variable goes on the y-axis, and the independent variable goes on the x-axis. So you always have to look at your original data and ask yourself, which variable depends on the other one? So let's go back and look here. Does the force depend on how much the spring stretches out, or is it how much the spring stretches out depends on how much force is added to the spring? Which one depends on the other one? Does the force depend on the elongation, or does the elongation depend on the force? Elijah? Yeah, the elongation depends on how much force you put on that platform there. So if you were going to graph this properly, you would make the graph like this. And you would plot your points and draw your best fit line. And it would come out like that. If you made your graph like this from your lab, kudos to you, because that's the proper way of doing it. However, even though that's the proper way to make the graph, it's actually more common to make it the other way. So it's acceptable if you made your graph the other way. There's some convenient aspects of graphing it the other way. So even though it's not technically correct in terms of graphing rules, it's the more common way .
Listen to it for yourself in the recording.
You'll still get a straight line. It'll probably have a different slope. So one of the reasons why this way is more popular is because when you calculate the slope of the graph this way, it has a very easy to see physical significance. Can anyone recognize what the slope of the graph this way will be equal to? Stephen? The spring constant, K.
So which one should we do for our
Either one. If you graph it properly, the slope still has physical significance. It's just not as easy to see. Guess what the slope will be equal to, Miss Sarah? 1 over the spring constant. Now I told you guys, when you write the equation of your line, I want to see 3 steps. The first step, regardless of which way you graphed it, I want you to write down the formula y equals mx plus b. And you would do that for this one as well. Y equals mx plus b. Then your next step, I want you to keep the y and the x, the 2 variables, but replace the m and the b with the physical values that you get from the graph. So for example, over here, you might get y equals 0.001 meters per Newton times x plus, maybe your graph actually went through like down here, folks. So then you would have to read this value right here, and maybe it would be like negative 0.02 meters. This right here is the slope. This right here is the y-intercept. So I want you to get the corresponding values right off your graph. If you were lucky enough that your data was so perfect and it went right straight through the origin, well then your y-intercept would be 0. And you could just drop it right then and there. But if your graph doesn't go through 0, show your understanding and put the actual value with units for b. Same thing with the other graph. If you graphed it the other way, you would say y equals, this time your slope would have different value in different units. It would be 1,000 newtons per meter times x plus whatever the y-intercept is. And again, maybe the y-intercept over here would be negative, or it could be positive. I'll make a positive sign up. Point. So once again, this is the slope of your graph. This is the y-intercept. But the last thing I want you to do is replace the variables with real names. Instead of just using generic x and y, put down the physical quantities that each thing represents. So for example, on this graph over here, what is actually being graphed on the y-axis? Repeat? For this graph right here, what's actually being graphed on the y-axis? What measurement did I graph on the y-axis? This graph right here, I measured force on the x-axis. No, I was just asking, what measurement is this right here on the y-axis? Elongation. Okay, so what does y actually represent? It represents the elongation on our graph. What does the slope actually physically represent on this graph over here? Careful, this is the tricky one. Krishma, any idea?
1 over 3.
Excellent. And Felipe, what did I graph on the x-axis right here? The force. And then what's the deal with that y-intercept? What can we chalk that up to? Yeah. That's like a systematic error. You did something wrong exactly every single time. So then we just cross this out and we say due to systematic error. If you graphed it the other way, what would the y variable be named? What did we actually graph on the y-axis there, Eric?
Force.
And this is a little bit easier way, Dan, because what does the slope represent if you graph it this way? Right, I'm just going to write it out. Spring constant. But you're right, it is K. And the elongation is on the x-axis. And once again, we could chalk this up to systematic error. You'll actually see the graph presented both ways. Sometime, like on the AP exam, you'll be shown the common way, and sometimes you'll be shown the proper way, and you just want to be able to handle both situations. And you know the common way, the slope equals the spring constant. The other way, the slope equals 1 over the spring constant. Now that we have this background information, we're able to answer the question, how is elastic potential energy determined or calculated? Let's look at a horizontal spring this time. Let's say we have a rigid wall and we have a spring connected to the wall. And let's say the spring is pulled on and when it's pulled on with a little bit of force, it stretches out, and let's say it's pulled on with even a little bit more force. So here we have no force put on it. Here a little bit of a force, and here an even bigger force. And let's say we wanted to figure out, hey, when it's stretched out this far, how much potential energy does it have? Now it's called elastic potential energy, but the symbol is PE sub S. Not for Solzinski, but for springs. And let's say we want to know, hey, how much stored up energy does that spring have? We know it has stored up energy if you let it release. Boing, 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 boing. Well, if I grabbed hold of that spring and I pulled it out, I would have to exert a force through a distance. Yes? Look at those guns, huh? And anytime you exert a force and you move something through a distance, the bottom line is, what are you actually doing? Work. Who said that?
I did.
JJ.
Steven.
Steven.
But he read my mind, so I actually did say it.
So it turns out that the potential energy stored up in the spring is equal to the work done to get the spring stretched out that far. Peter, do you remember the good old work formula, the defining formula for work? If I want to calculate the potential energy stored up in that spring, I know it's equal to the work done, but what is that work formula? Do you remember? Yes. But we run into a little bit of a problem here, folks. Because if we just put this whole force right in here, we wouldn't get the right potential energy. We wouldn't get the right amount of work. Can anyone read your physics teacher's mind or see what the problem is? Why can't we just use that final force? Alex?
Because it's harder to stretch out a string when it's already stretched out. You get the force at the end. Force in the time.
Say it again?
At the beginning, you can stretch it out really easily. At the end,
Exactly.
you need a lot.
Exactly. At the beginning, you didn't need hardly any force at all. Then in the middle, you needed a little bit more force. And then at the end, you need a lot more force. So basically, it's not a constant force. But it is a linear situation. So what's a poor physicist to do if they're trying to calculate a force value to put in there? You can't just use the final force. Oh, Elijah? Well, we're eventually going to get there, but we're not quite there yet. Okay? If you have a value to put in, but the value that you want to substitute in varies between 0 and some final value. Steven, you can use the average. Yes? And that's why really over here we should put a bar above the force, because really the work done is equal to the average force times the distance. Now the average force would just equal the initial force plus the final force added up divided by 2. And then multiply that by the distance the spring was stretched out. And by the way, that distance would be from here to here. So that would be the distance here. But what was the initial force? How much force was used at the very beginning? Krishma? None. 0. So that is just going to drop right out because the original force right here was 0. So that's going to go. And the final force, we're just going to call F. F is just going to be the final force. So if you rewrite this, you get the potential energy stored in the spring equals 1/2 times F times X, where F is just the final force used. Now, Elijah, what do we substitute for that final force used? K times the elongation. So you see this F right here, people? Right there? This F? We know that F is equal to K times X. Sometimes this is referred to as Hooke's law, because Robert Hooke was the first to figure this out. So we make that substitution in here, we get the potential energy in a spring equals 1/2 kx times x. Because the kx is substituted for the f. And finally, you get the derived formula for calculating the stored up energy in a spring. 1/2 kx squared. Dun da 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 da. I think it's like from the movies.
Oh yeah,
yeah.
That's Fox, right?
Yeah.
No, that is.
No, it's
It's Fox.
No, Fox. Fox.
Fox. Not that big.
So, ladies and gentlemen, if you want to know the hidden relationship between the force and elongation, right here, baby, Hooke's law. But if you want to know the hidden relationship between the stored up energy and the elongation, right here. Now, before we leave this topic, I want to go back and take a look at this first line right here. The potential energy stored up in a spring is equal to how much work was done to stretch that spring out. And by the way, it could also be equal to how much work was done to compress the spring. X could either be how much it's stretched out or how much it's squeezed in. But we talked about how to calculate work, especially if the data is given graphically. Fine. If you're given this graph here, we know the stored up energy in the spring is equal to the work done. Remember we did those 4 expert areas with the poster boards? If you're given a force distance graph, like the one on the right, what is the work done equal to, Stephen? Yes. So if you drop a vertical line right here, and you solve for the area in here, that area equals the potential energy stored in the spring. If you want, you could say that area equals the work done to stretch the spring out, which thus equals the potential energy in the spring. Either or. The easier way to do it would be the graph on the right. Because then what's the slope equal to? Spring constant K. Okay. let's look at some questions here. We have two examples of these pogo sticks. It's not the same exact pogo stick, though. The one on the left is not the same pogo stick as the one on the right. Now, if you're told the boy and the girl's weight, and in each case you're told how much the spring gets squeezed together, which is still called X, you can easily calculate the spring constant in each case. So why don't you two over here on the right figure out the spring constant for the boys' pogo stick. You guys over here calculate the spring constant for the girls. Keeping in mind that the force exerted on the spring equals the spring constant times the elongation. This here is the force. This is here is how much the spring gets squeezed in. It still has the X value. Felipe, did you get an answer for the spring constant for the boy? Units? And what about the girls over here? Brandon? Anyone over here do the girls? Brian? How much? 904? 940.
I'm doing stick fix here.
Yeah, so that would be newtons per meter.
Ouch.
So the boys' pogo stick might be a little bit heavy duty, has a stiffer spring. I know, like, I can't jump on my kid's pogo stick because it automatically, I hear it, like, it smashes it too far down.
Do you have your own pogo stick?
No, the kids have theirs. Now, if we wanted to calculate the potential energy stored in each spring, if you're given the boy's weight and the compression, the X value, what formula would we like to use this time? Iris?
One half the X.
Exactly. So sometimes you're given this information here, you're given the force, and you're given the X value, and you're asked to solve for the potential energy stored in the spring. So you got to remember, it's a two-step problem. First, use these two values to get the spring constant, and then you could go and use the potential energy in the spring formula. Yes?
Don't you just use B equals 1/2 of X?
You could do that too. Very good. Kudos to you. Good job. The units should work out. You end up getting joules. Did anyone get a value for the boy? Stephen? 102 joules?
No way. It's 20.4 joules.
How much?
20.4.
Oh. Never mind. Indeed, it is 3.4 joules.
And what about the girls?
15.
How much?
15.
Come on.
You get the square there. Don't forget the square.
Or you just do FS. I mean, what FS?
Alright, we're going to skip that one here. So, elastic potential energy. Elastic potential energy is the energy stored in a spring if it's stretched out or compressed from its equilibrium position. What's that? What do you mean by perfectly elastic? Yeah, if it makes a sound, there's some sound energy loss. If in actuality, the spring will heat up, so it wouldn't be perfectly elastic. Depending on the circumstances. How can the potential energy in a spring be calculated? That was today's lesson. There's two ways. What's one way? Shaitan, one way to calculate elastic potential energy.
1/2 the K.
That's it. And what is the other way to calculate elastic potential energy? Sarah? From the graph. Area underneath the curve. Thank you, you too.